Hello everyone, my name is Denise Jimenez Guzman. I am a physics engineer student at the Universidad Autónoma de Ciudad Juárez, and today I'll present our work title, Fluorescent Iron Sensing Using Surface Functionalized Silver Nanoparticles, conducted in collaborations with Dr. Enrique Sánchez Mora at the Benemérita Universidad Autónoma de Puebla. So, to begin, let's explore why this research is important. Iron plays a vital role in biological processes, such as oxygen transport, growth regulation, and cell differentiation. However, while essential in moderate amounts, excess iron can be toxic, making its monitoring in both water and biological media crucial. In recent years, metal nanoparticles functionalized with amino acids have emerged as promising alternatives, offering improved selectivity and sensitivity for metal ion detection. Among these, glutathione is a tripeptide containing thiol, amino, and carboxy groups, which not only stabilizes nanoparticles but also acts as an active site for metal ion bonding. When conjugated to silver nanoparticles, these functional groups enable selective coordination with iron 3 ions. The interaction triggers electron transfers between glutathione and iron 3 ions, resulting in measurable fluorescence quenching effect. This property forms the basis of our detection platform. Our goal was to synthesize, characterize, and apply glutathione functionalized silver nanoparticles as fluorescent sensors for the detection and quantification of iron 3 ions in aqueous solutions. With this objective in mind, let me now walk you through our experimental approach and the methodology we follow. The synthesis of our nanoparticles was achieved through a combined chemical reduction and UV irradiation approach. We combined, under vigorous stirring, 5 ml of 25 mmol silver nitrate with varying volumes of 25 mmol glutathione. The initial pH of the mixture was acidic, below 5, which we adjusted to pH 5 using sodium hydroxide. The solution was then irradiated with UV light for 30 minutes, and the resulting colloidal solution was stored in cool and dark conditions. Once synthesized, we proceed to the characterization stage. UV spectroscopy helps us identify their plasmonic properties. Dynamic light scattering was used to determine their average size, and Z potential measurements confirmed their surface charge and colloidal stability. For the iron detection phase, we use a fluorescence spectrophotometer, and we prepare samples by mixing a fixed volume of glutathione functionalized silver nanoparticles with a pH buffer and deionized water in a cuvette. We then introduce varying concentrations of an iron 3 solution and monitor the fluorescence response. With our samples synthesized and characterized, we move on to evaluating their performance. And here are the results we obtain. We obtain average particle size of 3.9, 6, and 14 nanometers for glutathione functionalized silver nanoparticles. All samples exhibited negative surface charges ranging from minus 74 millivolts to minus 99 millivolts, which we attributed to the deprotonation of carboxylic acid groups in glutathione. Here, we can see an image of the samples under UV light. Now, for their optical properties, under 370 nanometers excitation, we observe a strong emission peak at 430 nanometers, an emission absent in the precursor solution. We also found that the fluorescence intensity increased with higher glutathione concentrations. This fluorescence is the basis of our sensor. The addition of iron 3 ions causes a proportional decrease in fluorescence intensity. In other words, we observe a quenching of the fluorescence due to interactions between iron 3 ions and the functional group of glutathione. This quenching behavior allows us to build linear calibration curves for quantification in the micromolar range. The system showed remarkable pH responsiveness. In acidic conditions, pH 4, we detected the widest concentration range, from 40 to 200 micromolar, while alkaline media, pH 10, enable ultra-sensitive detection down to 0.6 micromolar. These findings lead us to several important conclusions about the potential of this method. In summary, increasing the amount of glutathione during synthesis results in larger nanoparticles and a slightly reduced colloidal stability. The glutathione functionalized silver nanoparticles were highly responsive to pH changes and to the presence of iron 3 ions. The sensing mechanisms relies on fluorescence quenching, which is caused by the interaction between the iron 3 ions and the carboxyl and amino groups on the nanoparticle's glutathione shell. Nanoparticles synthesized with more glutathione show greater sensitivity, allowing us to develop a highly responsive sensor for iron quantification. To conclude, I would like to acknowledge the collaborative efforts that made this research possible. I also gratefully acknowledge the support from the Vicerrectoría de Investigación y Estudios de Posgrado de la UAP. Thank you for your attention. I will be happy to answer any questions you may have.